Okay, so a couple of handouts floating around, so please make sure to pick them up. Maybe you can just pass them around. Um, so just for this particular lecture, I'm distributing the handouts uh, for everyone, including those who are on the waiting list. But in future, I'll only be bringing 30 copies, which is the class size. So if you are uh, still going to be shopping around, then make sure to print them from the Piazza website. Okay, so let's start on the logistics. Um, so this is 202A slash 213A. Information about me. I'm going to be doing my office hours on Mondays 3 to 4, Wednesdays 4 to 5, Fridays 4 to 5. And if none of these things work, then write to me, set up a time. I am usually either in my office or my lab, so you can also kind of try to reach out to me. If you want to send me an email, make sure to put 202A or 213A somewhere in the body of the email, because I use them to make sure that mails don't go to Gmail's overly aggressive spam box. In case you need to locate me, my assistant, she also sits on the 6th floor of this building. Okay, so about the course itself. So just going through some of the logistics. So this is intended to be kind of the opening course, or in embedded systems. By opening, I mean that we don't expect any other prior graduate background from you. The course, roughly speaking, is about computing systems that connect with or tie up with physical systems, and to do interesting things like sensing, control, things like that. There are a variety of names under which this broad area is referred to. Embedded computing is one of those. Things like cyber physical computing, Internet of Things, a whole bunch of things which kind of dance around the basic concept that computing becoming part of our physical world. Um, so this is kind of as contrasted to much of traditionally in computer science, which has been about creating powerful servers or workstations or kind of more general purpose computing environments. Um, there are some other courses. So I teach a follow-on course in spring whose focus is on energy aspects, low power aspects of these type of systems. So that we don't go into in this class. There is also concurrently this quarter is EE202C, which Bill Kaiser teaches, and it's kind of more for design-oriented course focused on wireless health applications. Um, so the focus of this course this quarter, I decided to kind of focus on that those subtopics of embedded computing which kind of relate to these devices being interconnected. And it's kind of often currently in the media, the buzz phrase for this thing is Internet of Things. But really, what's kind of my way of saying is that we're going to focus on things which, as opposed to standalone embedded systems, are relevant to embedded systems that are interconnected and on the internet, and things that arise. So there are certain issues that kind of come up. Obviously, connectivity being one. Security issues become different when you start looking at um, uh, things that are interconnected. There's a definition of IoT which I lifted from Wikipedia, but it's basically saying embedded computing, which is on the internet. Embedded systems itself is a pretty old phrase, embedded computing, embedded systems, and it basically refers to computing systems that are intended to not be our general purpose computers, but rather be part of some bigger system. So things inside appliances, inside vehicles, inside kind of boxes which are squirreled away in somewhere in the closet, or kind of out of sight, out of mind kind of situation. They just kind of do their work in the background. Since they process physical signals quite a bit, so their design tends to be dominated a lot by things like constraints on timing. Physics of the physical system they're interacting with plays an important role. They also come with more significant constraints on size, volume, cost, power consumption, things like that. By contrast, general purpose computing, that's kind of primarily intended to interact directly with us doing things like word processing or software development and things like that. Not to say that parts of our general purpose computing systems do not have some physical attributes. They do, like when we type on a keyboard or move a mouse, or of course a lot of our devices have cameras and microphones. So there are elements, so this boundary is kind of not really a strict one, but sort of when you see something, you can kind of say, okay, it's more on the embedded side of things as opposed to general purpose. But there's certainly some things which embedded computing community has kind of addressed more of. And I guess historically, this area has been something which is at the intersection of EE and CS. So you kind of see researchers from both sides kind of working on it, which is why this course is also kind of cross-listed. Internet of Things, that's, like I said, this area does get referred to by many different names, and currently kind of the fashionable term is Internet of Things. And basically what's happening is kind of a general trend. I'll touch upon it more in kind of the second set of slides that I have, which is it used to be, internet when it started out, it was a couple of, or 2 or 3 kind of interactive terminals. One of them was right in this building, a couple of floors below. But now if you look, kind of the edge of the internet, if you may, is dominated more by devices, okay, not by what we normally would think of as a computer with kind of keyboard, display, and stuff like that. So what's happening is it's kind of a convergence of kind of a bunch of things that are happening, but main thing is that embedded devices began to get network interfaces, and meanwhile kind of the network sort of percolated everywhere, and the end result is kind of we basically have at this stage an internet which really is dominated, whether you look at number of boxes or CPUs, dominated by what one would call as embedded devices. They sense things, they ship data, they analyze the data, perhaps in assistance with stuff in the cloud, they make inferences like what's happening in the world, do some state estimation, run some control algorithms, these kind of things. And we kind of sort of lots and lots of things which we kind of increasingly are seeing, personal robotics, autonomous vehicles, they're all kind of examples of that category of system. Whole bunch of application domains are being impacted by it. Health, buildings, transportation, things like that. And I guess the assertion, which we'll explore in this course, is that there are certain things that this category of system presents which are kind of either have a unique spin on them or are unique when we do this thing, as opposed to if you were to just look at a traditional sort of computer system curriculum, if you may. So looking at the course logistics and all, so prerequisite-wise, like I said, this is intended to be an opening graduate class, so no undergrad, no graduate prerequisites are there, but I do expect that you would have kind of an undergrad degree, which is either kind of a computer science engineering type degree or an EE degree with a computer engineering kind of focus on it. So you should be comfortable programming, needless to say, and you should be comfortable analyzing stuff. Okay, these are collectively across a whole bunch of courses you would probably accumulate this thing. And I often get asked, hey, this course is too EE for CS. All I would say is wake up, look around computer science departments everywhere. Even though I may be in EE, the course here is in EE, but a lot of similar courses are just sitting in CS departments. It's a changing face of computer science. And those of you who are EEs and say, hey, too much software, I would also say wake up. Most of the hardware around you is actually, hardware is a tiny part, and whatever it is being done in China or somewhere away from this country. The interesting stuff happens when software meets hardware. And one skill, your life-making skill, if you may, can have is to be proficient at software. So take it as a challenge. Now, having said that, I'm not going to babysit anyone in terms of programming. This is assumed that you would know, so those of you from EE side. Course registration issue. So seeing that maybe a dozen of you are standing in the back, and so this is an important one. So for a variety of reasons, but foremost being that this is a course where there is a significant amount of sort of project flavor, if you mean, is there. So the hard cap, I'm not going to take more than 30 students. And as of this morning, there were 29 enrolled in the class. Usually some people drop out, so I'm pretty sure there'll be some seats that will open up. So as spaces open up, I will hand out PTEs. There's a criterion which is kind of listed out here. I sort of emailed it around as well. But additionally, just to give some of you are really, really motivated and bring some unique experience, which will add to the class. I've also sort of floated this Google form that you can fill out, but don't put things like I'm a hardworking student and things like that. Those are pretty commonplace. I'm kind of looking for something which is interesting about your background, which I feel having you in one of the project groups and all will add value to the class. Okay, so that's the kind of thing that we're looking for. Fill it out. Right now there's one spot, but usually by the end of week 1, after you have seen through all these slides, some people do drop out. So yeah, I don't think in recent years this class has actually exceeded or even hit 30, other than 2 years ago when it was 55, when we didn't have, by mistake, we didn't have a cap. So in any case, 30 students is what's going to be. If you are course shopping and auditing, so if you're course shopping, make up your mind quickly, because if you are enrolled, then you are hogging a spot, and it's going to prevent others who are interested sort of coming aboard. In any case, while UCLA, those of you who are new to UCLA, you may not be aware of this, but UCLA, interestingly, allows graduate students to drop classes until the last day of the 10th week. So you can literally pick your grade. Now, that doesn't make it right, and EE department in particular frowns upon it quite a bit. Essentially, we put you on a blacklist. So don't sort of push on that. I mean, there could be genuine cases, medical emergencies or something, but verifiably, if you can verify and all. But other than that, I mean, just make up your mind. Certainly by 4th week, but if at all possible, do it before that. And I'm going to do my best to force your hand. Okay. When you drop the class, please do officially drop it. So oftentimes, kind of you forget and you're kind of still enrolled, but I have no way of knowing that really. So I don't take attendance in the class other than today. Please unsubscribe from the various Piazza and anything else that you may subscribe to. I will not have auditors. Sorry. Again, the intent is I do want to have kind of a cohesive small group that so that the course can be well taught, as opposed to kind of just the dynamics of the questions and answers kind of just disappear when. So no auditors, unfortunately. But if you're shopping around, hang on for a week or so that it becomes clear whether students are dropping out or not. Questions? Okay. CS213A versus 202A. So in previous years, we used to have students in both sections, and it kind of made management of the class rather tricky for me, because sort of 2 sets of things going on. So this year, every student, whether CS or E, is enrolled in E section. And this is not unusual. CS does the same thing, which is whenever they have cross-listed courses, the E sections are closed and everyone registers as a CS student. In terms of your CS 200 series requirements, just talk to Steve Arbuckle, but basically it's the same course. It's just that all enrollment is going to be through 202A. Okay, talking about grades and components. So there are basically going to be 4 things in the course. Bunch of homeworks, which kind of span. Some of it would be kind of more traditional problem solving, but some of them would also be to force you to learn about some of the platforms that and sort of getting your hands dirty with embedded systems. Each one of you, and this is another reason why the cap of 30, will have to make a short presentation. Most of them will be kind of like mini tutorials on some specific technologies. The kind of idea is that this is my way of kind of getting everyone to explore a very rich space out there. I mean, there are tons of companies and all which keep producing some cute little technology, new standards coming up and all. And it's not lecture-worthy material for me to kind of go with, but I think through you, we all get to learn about it. So the idea is sort of usually on their websites and all, they would have some stuff about what the technology is, maybe a little tutorial, kind of the hello world equivalent of embedded systems. things like that. And then occasionally I'll also have kind of some researchy paper. But the idea is 15 minutes in class, maybe 8 slides, 10 slides if you speak fast. Hard limit because 30 students times 15 minutes is a fair bit of the time out of the whole course, so I do need to keep it controlled. Actually, it's going to be 12 minutes of presentation and 3 minutes of Q&A. So you really, I mean, I rarely encounter any paper whose key idea or technology whose key idea cannot be expressed in 12 minutes. I'm sure most of you are aware of this concept of the elevator pitch. Anyone? What is that?
Pitch that you do to investors to get funding.
Right. And you're riding from one floor to another, and you have to get someone to pony up a few $1 million during that elevator ride. Okay, 12 minutes is many elevator pitches. Okay, so you should be able to get the key idea right across. Okay, so it's sufficient time for the kind of topics we'll pick and the papers we'll pick. Topic survey. This is the third element, and again, grading percentages on the right-hand side. So the idea out here is that this is kind of like a traditional term paper. You'll have to select a topic with my consent and then do an in-depth survey of that. Essentially, what's the state of the technology, what are the challenges, what are the directions, kind of oftentimes like on Wikipedia or Scholarpedia, these kind of places, you'll see these in-depth articles, which basically for someone new who wants to learn about that topic can go there and use that as a resource. It will be supported by some primary and secondary references, some analysis from your side, things like that. It's not a summary. It's kind of intended to be a survey paper written by you. And finally, and that's kind of the roughly half the course, a course project, generally intended to be done in a team, but if you work off campus and all, then occasionally people do decide to do it individual. So the idea is this cannot be a survey because we're already doing a survey. So this is where you have to create something, okay, or sort of contribute something where you build something or analyze something or get some new kind of data or things like that. So that's kind of the intent. And at the end of it, you have to do a report plus a in-person demo / presentation. So this is really kind of there's no final exam and no midterm exam as you can gather. Kind of this is what sort of serving the final exam purpose. Any questions?
Topic survey? Do you mean like secondary research, writing a secondary research paper instead of just going to talk to somebody, ask questions, taking their answers, that kind of survey?
Yeah, no. So this is not intended where you going around and kind of doing an in-person interview or anything. The idea is kind of identify. Let's say, for example, decided I'm going to do survey on mobile operating systems. Okay, so you're going to look for. I mean, clearly there are 3-4 of them which are very relevant. So from Google, Apple, Microsoft, and so forth, they will have the technical documentation and all. But then others write about them. There are websites which analyze these things, and there are technical papers which kind of study the performance and all. So kind of in early stages, you'll kind of do the landscape and then identify some that would constitute kind of the primary reference, and then some additional things for minor points would be supporting things. So. Any other questions? Okay, those of your E students, which is most of you actually, roughly 80% of the class is E. If you are doing an MS, you also would be given a comprehensive exam grade. And unlike other classes where take one question and use that as the comprehensive exam grade, I don't do that, and I instead use your course grade as the comprehensive exam grade. So there's no comprehensive exam question. It's the totality of your performance in the class that would be there. So next few slides are a bit more stuff about survey articles, so that hopefully should kind of answer the question you had. Main point is articles should be original writings, not intended to be copy a para from here, copy a para from here, and kind of create a new assembly. I mean, that's not a survey paper. These should be your own words where you kind of bring some insight based upon the material that you're collecting. I like the style of articles at Scholarpedia. Anyone heard of Scholarpedia before? No one. So Scholarpedia, as the name implies, is for it's kind of the more serious version of Wikipedia, intended to be on more researchy topics, mostly focused around computing and engineering topics currently. The main thing is these are very thoughtfully written articles by kind of well-regarded individuals in the field. So unlike Wikipedia, whose quality can kind of be pretty shaky, these are usually longer, more in-depth, and kind of just so certainly sort of take a look at some of those. So the idea out here is I don't want you to submit a PDF file and all. I want you to create a little website along the lines of these things. Okay, so that we just kind of link in from the course. This also, my intent partly also is that I want you to begin to learn how to convey and communicate via these newer methods. It's very easy to write a Word file, dump a PDF, send it to me, okay, but that's not how much of the communication now happens in our research community, professional community, and all. So getting used to kind of using the more modern tools is relevant. There are very easy ways of doing it. Just explore a little bit. In any case, this would be due during the last week of classes, so the 10th week, basically 10th full week, on the Monday of that week. Again, done individually. Short presentation. So it's intended to be a short mini tutorial or kind of a research result from a paper kind of talk. 12-minute talk plus 3 minutes Q&A, which pretty much means that you should probably have like 8 slides or so. Maybe if you talk really, really fast, you can squeeze a couple more, but unlikely. It could be, for example, I might say there might be some new processor which has come out, which is pretty cool for some aspect of embedded system. So it could be, do a little talk on that, what its capabilities are, things like that. Or maybe there is some new communication standard or a new cloud service catering to IoT. So those would be the kind of the topics out here. And occasionally it could be some cute little paper or some conference. There will be no bidding for these topics, so because it soon runs into a chaos. I used to do that where I'll ask, okay, tell me which paper you want to do and all. I'm just going to assign, okay. And I think the benefit also is it will hopefully take you outside your comfort zone, okay. So I will start making them. We'll start doing it from week 3, and I'll do the assignment for any kind of a week before. So basically, by early next week, I will hand out the set of topics for the following week, and among obviously restricting myself to those who are enrolled. And that kind of brings me actually a thing that I forgot. So there is this little attendance sheet on which I have all the names of students who were either enrolled or waitlisted as of this morning. If you are here, place it, just initial against your name. If your name does not appear on this, just add it to the end, providing me the same information. So maybe we can start from you and you can circulate it. It's sorted by alphabetical order, I think. So last name. Okay. Occasionally in homeworks, I will ask you to read a paper and critique it. And what I mean by review or critique it, and what I mean by that is not to summarize it, because I would have read the paper, I know the paper, so that's not the intent, and everyone else would have. The idea is that you would focus on what its weaknesses and strengths are, and what could be further directions you can kind of go with that work, new directions on that work and all. So we'll have a few of these. Again, kind of those of you who are headed to PhD or PhD students, being able to analyze others' work is a very critical skill, and this is something that I hope to accomplish through these. These would be like 1 to 2 pages type critiques, and for any such material, I will just ask you to follow. I've given a template out here. This is standard ACM template. We'll just use that so that we can have consistency of font size and line spacing when we talk about number of pages. Course project. Course project, the intent out here is to dig deeper into an area. And like I said, surveys are not acceptable, rather you create something, okay? And they're roughly speaking, very broadly, they're kind of 3 different kind of projects that sort of one could pursue, or people tend to pursue. So one is, given the nature of this, there are projects which are about creating a new type of system, okay? Some new, I mean, the world of embedded and IoT is just full of sort of all sort of companies and people creating new systems, new capabilities and all. And that's certainly fine. The main thing out here is that it better be something which is interesting. I mean, providing yet another version of a concept which has existed many times is kind of not doesn't make for a very interesting thing. Another cluster project is where you take some element of a embedded IoT system and then do something in deep there. So what I mean by that is it could be perhaps a new kind of a sensor, maybe a new protocol, maybe a new cloud service which provides one of the building blocks for others to use when they're designing a system like this. Or it could be a new tool and all. And then final category of projects is where you do some performance analysis, performance measurement. So you kind of take a system, measure data, or you model it and theoretically analyze it and try to come up with some model prediction about relevant to these things. So like for example, it could be maybe I have a couple of different technologies which do the same thing. How do they compare with each other? Like for example, how much power improvement does Bluetooth LE, low energy, brings over, let's say, traditional Bluetooth, or things like that. So these are examples of, or you could even pick a specific technology, like I don't know, some of these beaconing technologies that are emerging, how well they do. Again, theoretical modeling, experimental measurement, those kind of things. Again, I would urge you to do these things to the extent possible in groups. I think the only thing is, as you form groups, make sure that your partner is committed to the class. You don't want to be caught off guard. So trust is probably the most important thing in life, and so is coursework. So that's one aspect. The second thing is, don't have a partner who is a clone of yourself, because then you're not benefiting. So if you're strong at hardware, pick someone who kind of complements your skills or things like that. Okay. So as you look around for partners, do that. You can use Piazza for this. So let's say a project idea, you could throw around, I'm looking for someone to do a project along these lines, and anyone interested, and kind of form teams among yourselves and try to do it sooner the better. Excuse me. So in terms of the project timeline, looking for projects to be finalized by the end of week 3. That means topic, an abstract, and a team, some general sense of where you can do it. And obviously that means that before that you have spoken with me and kind of consulted me, or sent electronically or in person. Then you would create an initial web page. Google Sites works very well for this thing, or it could even be like a folder on Google Docs with a website with a HTML file and a bunch of other supporting documents. And then that you keep use as your kind of project management place. You keep adding material there, update it, interact with me over the course of the project, basically. So, and then what that would mean is, by the time the quarter begins to draw to close, you would have material to kind of come up with the report and presentation relatively quickly. Reports are due during the exam week by Wednesday. Presentations would be scheduled starting the weekend after the 10th week and then through the exam week. Okay, so I'll just set out a bunch of time slots. You sign up for it, and essentially I give 30-minute slots during which you can do presentation/demo. By presentation, I do mean something where you'll have some slides and all. It's not meant to be a conversation. Just you sit on the table and talk with me. It's meant to be a presentation. So the grade for the project would be split this way. 40% towards the quality of work and effort. I do normalize it to the task you undertook. Okay, so for sort of, if it's a more challenging problem that you decide to take, the quality of work may not turn out to be as good. I mean, if like maybe you decided to address an open problem is something easy, then of course I expect more polish. Oral presentation/demo, 20%, final project report, 20%, and then very important interaction updates you have during the quarter with me. If the only time I see your face is at the beginning of the quarter and end of the quarter, then you get 0 on this category. Okay, so the intent out here is that you interact with me. Project proposal and final project presentation, everyone does it. It's the middle that matters, and that's what decides the success or failure of most projects. So very important that be the case. In some cases, I will have one of my PhD students act as your project mentor, in which case you can interact with him or her, and that's fine. I kind of exchange notes with them. So, but you have to talk to one of us. Questions? No one? Okay. There are more project guidelines. I'll let you read on your own. Excuse me. I've also kind of included sample projects from previous years. Bear in mind, though, that in the older instantiation, this course often used to focus on standalone systems. This time around, I would like you to go after projects where internet connectivity kind of plays a critical part to the functionality of the system. Okay, so a whole bunch of them going back 5-6 years. Okay, course on the web, UCLA. In engineering, we have switched to using this CCLE, which I myself am trying to learn. It's kind of a very different system than what we used to use last academic year and before. But this is kind of our official course thing. If you are enrolled, it should already be on, and I guess if you're waitlisted, same thing. I'll use it to post assignments, for you to submit assignments. So every submission will be online. This thing allows you to upload stuff, archive files, and things like that, and for grading. I will not use it for announcements and all, or for some posting course material. I'll be using Piazza for that. If any, those of you are new, Piazza is being used by many courses, and I have been using it for the past couple of years now in my courses, and it works out pretty well. I'm a lot more responsive, and kind of the nice thing is that it has a very much more kind of collaborative style, as opposed to kind of a forum where people keep posting and after a while you kind of tune out. Okay, so just the level of engagement tends to be much better. So I'll stick with using that. The forums on CCLA are kind of a bit archaic. So that brings me to the other element, which is Piazza. You should have already received the invite, and I noticed there were 3 students who I sent the invite and they didn't sign up, so I guess they're not in the class. But I think there might be more of you out here, so you can sign up for it, at least during the shopping period, so that you don't miss out on the announcements. No textbook, but I have listed a bunch of them that if for some topic, for homework or something you want to hit, many of them are in the library. There are a whole bunch of courses, various places on topics dancing around this. Whole bunch of conferences and journals and stuff like that. Okay, so now comes the bad news. So no textbook, that's great. Textbooks are pricey and not very useful for a course like this, because by the time they are written, they're obsolete. So instead of that, what you need to do is you need to acquire a couple of hardware platforms, which would be the core for the homeworks, as well as be the basis for the projects that you do, if your project is kind of experimentally oriented. So if you look at kind of a typical Internet of Thing type system, what you really have is kind of 3 very distinct components, if you will. So one is what you can say is kind of a device layer. Okay, it could be embedded as in stuff inside objects in our surroundings, wearable like smart watches and Fitbits and these kind of things, and then also in many cases implantable. There's a lot of work going on where kind of for a variety of purposes inside humans or animals, kind of stuff gets put with wireless communication outside and all happening. So there's a device layer. And this presents, as you might imagine, much more resource challenge, cost sensitive, low-end processors, perhaps even 8-bit type processors and all, very cramped programming environment, maybe even diving down to assembly and stuff like that. Then the middle layer, which is sort of just the gateway layer, if you may, and I'll talk about in the next lecture that why it is almost always there in some shape and form for very critical technology reasons, but usually at this stage you are looking at more well-endowed hardware, software which is has capabilities kind of like what we are used to. So it has a networking stack. It would have some sort of multiple processes, concurrency, all those kind of things. Kind of more. So you start getting closer to a general purpose environment, but you may still have sort of support for some sensing, some real-time kind of aspects and things like that. And then finally, in recent years, I think that's been kind of a very transformative thing for embedded systems. That is, they begin to hook up to various services in the cloud, ranging from something as simple as storing data out there to the data getting analyzed to some stuff happening there which then takes action and informs users or controls machinery. So you begin to close the loop. So it's not simply data flow this way, but also services in the cloud then beginning to control stuff. And we see them around. I mean, if you at all kind of play with these technologies and all, I mean, a lot of products which are targeted at homes and all now have these kind of capabilities, right? I mean, I can remotely arm the security system in my home or kind of check the status, open of my garage door, things like that. So there are all kind of things where there's a bi-directional stuff which is happening, and I think part of the reason is that we want to interact with deeply embedded stuff wherever we are, and even wearable stuff, which is others like in a health setting, maybe an old person wearing some wearable device, and their caregivers or doctors or family members might want to kind of interact with them. So cloud as kind of this mediator of information exchange and as the place where a lot of interesting analysis could be done is becoming kind of critical part. So with that, asking you to get two pieces of hardware, one in this layer, one in that middle layer. The cloud part is, of course, there's plenty of free stuff out there, so don't require anything. So for the embedded part, so there are many things out there. Besides the one out here, anyone heard of any tiny embedded devices or used one?
Raspberry Pi.
Nah, Raspberry Pi is more like a gateway, right? I mean, it runs Linux and all.
Launchpad.
Huh?
Launchpad.
Say it again?
Launchpad.
Launchpad, yeah, okay. Launchpad, okay. What else? Tinsy. What else?
Embed.
Embed is already here, right? Okay. So, but these are examples, okay? Arduino, which is probably the most well-known of this category, and there are a bunch of stuff like that. Since this is intended to be a class where I want you to dive under the code a little bit, so I decided not to go for things which are intended at application developers like Arduino, which is kind of more very simplistic form of programming. So Embed is a platform I like quite a bit. It's ARM's official platform now. They kind of started with NXP, a company which in turn was Philips Semiconductors long ago. So it's more, it's closer to the engineering kind of way of looking at these devices, more powerful. You can do a lot more stuff with it. It comes at various price points and all, ranging from $10 to, I think the costliest one I have seen is like $80, something like 75, $80. Okay, anyway, so this one is from Freescale, $15. It has a 32-bit ARM M0 Plus processor, so one of the most power efficient processors which is out there. Very modest amount of programming memory and RAM. So I mean, in this day and age of like, I mean, I don't know, my laptop has 16 gig of RAM. I mean, this is like teeny. So mindset when you program these things very different. Now, what makes this thing interesting is supported by this thing called Embed, which started out as essentially an online toolchain. So literally, you do all the development in the browser, and then you plug in your device through a USB cable, in this case, to your laptop, and then you just save the file. It appears as a USB disk, and you kind of save it there, and then unplug and hit the reset button, and you're good to go. So it kind of took care of the most nasty problem that beginners in this area have it, which is setting up the tool chain. Okay, depending upon your platform, Linux is usually very easy, Mac almost as easy, Windows always used to be the pain. With something like this, the playing field is leveled. Of course, there are issues then. I mean, there are things that you could do with a tool chain which is on your computer, which you cannot do it when it's in the cloud, but it works very well. More importantly, a very nice community with lots of components you can use. You're looking for some little piece of software, someone would have done it. Okay, so maybe not as rich as Arduino's, but almost as rich and certainly a lot more powerful. I mean, this is where the real engineers go. Okay, Arduino's is where the artists go. Apologies to those who are into arts. Okay, so to get this thing to work, you'll also need a USB A to Mini B cable. You probably already have it because so many. I mean, I probably in my home have a collection of 40, 50 of them, and I keep throwing them away because they come with every little thing I buy, and then you keep replicating. Okay, so you probably already have it. If you don't, on Amazon, I found it for less than $2 and all, so pretty low-cost stuff that you can get. You should go to embed.org. This URL, actually, I'm thinking about it, may not be quite right because they did a website restructuring. Now, one thing that I noticed, at least I encountered last year, that the stuff that I bought comes with a firmware which needs to be replaced. It needs to be replaced with a firmware which actually works with embed. So you have to follow the instructions and kind of do it. It doesn't take long. For me, the hardest part was that I needed a Windows PC running 8.0 or lower. So that's just something to keep in mind. You may have to sort of seek someone's help to locate that thing if you don't have. I recall, at least as of last year, the firmware update instructions were not working with Linux and Macs, but that may have changed. They were supposed to work, but there was some driver issue. The other thing is, you would notice this board just has holes out here, and some of the stuff may require you to kind of connect things to it. So what is useful usually is also to get headers, kind of those little pins that kind of stick out, and solder them to this thing. So that will make hooking things up to the board much easier than otherwise. My lab has soldering iron and all, so you can visit it and kind of solder, but make sure you know how to solder. If you don't, I've given a link to a tutorial, and you can seek help from one of your classmates. Sure, plenty of you are comfortable with that. What this board does is, it gives you a whole bunch of pins out here, which include things like analog in, bunch of different kind of serial connections that are often found in sensors and devices and stuff like that. There's a couple of UARTs, SPI, I2C, these are kind of the three most common things. The other thing, the reason I picked this board over other embed boards is that it already has some sensors on board, which is why it's slightly more expensive instead of a $10 version. It has a touch slider out here, and it has a magnetometer and an accelerometer somewhere on the board. Okay, so it lets me give you a homework assignment where you don't need to connect any external sensors. Okay, so it kind of is a lot easier to get started with. But other than that, I mean, it's like any other embed platform. If you already have some other version of some embed, like last time I recall some of the students already had one other version, you can use it, but then you may have to find some sensor, which may actually turn out to be more costly and painful than just kind of getting this. Okay, the second one is the gateway platform, and this is intended to be a mid-level Linux Android type device with a network interface. Now actually on this one, your Android phone could almost work. The only problem is it usually doesn't have any GPIO. Now, having said that, I do know that there are some companies that do make little hardware boards which can hook up to the USB port on the Android phone, and then you can get GPIO, and you could certainly do that. Then you will have a complete platform, but then you better be comfortable with programming on Android. The course instructions and all otherwise are going to assume that you have one of these boards which comes with an embedded variant of Linux and all. So Raspberry Pi, I've given some choices out there. Raspberry Pi is probably the most well-known. There was someone who had said that also. I would recommend that. The main thing is that there is a much bigger community around it. does have some limitations relative to other options. It has no analog I/O, but I don't, at least for the main class, I don't expect to use that. But your project may benefit from having that. But then there are ways around it. You can buy a analog I/O board. The cost of this usually runs around $40 or so. Plus, you will need a USB cable. Again, you probably already have it. You'll need a micro SD card. Probably don't have it. Micro SD cards are not very common, other than maybe you have in your phone. Plus, for debugging and all, the so-called console cable. So what these embedded platforms do is when they have serial ports, they are not RS-232 ports. RS-232 ports operate at plus minus 12 volt. The serial ports operate at a lower voltage, and they don't want to put the cost and effort of putting an RS-232, which is what kind of our computers speak, and in any case, RS-232 ports are essentially disappeared. So what these guys have is what is called as low-level voltage things, essentially a bunch of pins, and then companies sell cables anywhere around $6-7 to $10, which basically connect to USB port on your computer and connect to those headers on these ports. Many companies make it. You just look for like Raspberry Pi USB cable or something like that. You kind of find that. This is how Linux running on these platforms offers this console. So the console is on a serial port, and essentially then it hooks up to your laptop or computer, and then you can run a terminal emulator out here. So essentially your terminal window out here is the console for this embedded device. Very useful for debugging and all. It's not required though, okay? For simple stuff and all, it can just work because you can hook this thing to Ethernet and then remote log into that. But if you want to do anything deeper than that, that is like change the firmware or stuff like that, it's useful to have that cable. Option number 2, which actually I like more, is something called BeagleBone Black. It comes from TI, again a very rich community around it, more powerful processor and all. It's more intended for embedded type usage, so lot more GPIO, you can analog input output, those kind of capabilities and all. It also so in Raspberry Pi, the GPIOs are out here. In case of this, there are a bunch of connectors here. These are female connectors, so it's easier to connect to. There are a bunch of companies which make specialized boards that sit on top, a bit like Arduino. So I like this one. They have a much better support, cloud services built around it and all. Its cost is higher, but then you don't have to buy some of the other stuff. So depending upon what you already have and all, eventual cost difference is $5 or so, but if you have some of those materials already there, Raspberry Pi is cheaper. So depends. You can decide. Many vendors sell these things. The SparkFun, Adafruit, these are a couple of companies which cater to the maker community, so they carry these things. Amazon usually has them. And I'm pretty sure LA is kind of plenty of shops like these in Los Angeles area. I know there's one in Van Nuys on Oxnard, just east of Sepulveda, which carries a lot of this kind of stuff. Fries, these kind of things, except that these stores tend to have higher prices, so it's probably better picking something online. I know Adafruit has them in stock because I just purchased latest version of BeagleBone myself, as well as Raspberry Pi. Another one, which actually is probably the coolest of these platforms, but the costliest as well. So Intel has this thing called Intel Edison, which is a credit card size PC. It has a dual core Atom on that. The key thing out here is it also has Wi-Fi and Bluetooth built in, whereas in these platforms you have to kind of add additional stuff to make that happen. The only thing is, and besides the cost, which is why I'm not going with it, it also, availability seems to be a little bit limited. It just came out, but it's a pretty cool platform. So for Raspberry Pi, if you pick up the Model B Plus, which is the current version. The main thing, nice thing about that, and which is why I think it's a better choice for this class, it has 4 USB ports. So you can really hook up a lot of stuff easily. So that's kind of a nice thing. BeagleBone has only 1 USB port, so it has more GPIO and all, but 1 USB port. For purposes of the class, this will also suffice, but Raspberry Pi may be preferred, and that was Edison. Then you need, so 40 bucks plus 15 bucks plus some cables, which you probably already have. Then final bit, some additional components. So we are going to be using these two platforms need to connect to each other, and we'll be using Bluetooth for that. So what you need in this particular case is, so if for the gateway you are using your Android device, then it already has Bluetooth. You don't need to do anything. If you are using Raspberry Pi or BeagleBone, then you would need to buy a USB Bluetooth adapter. I like this one from Amazon, 12 bucks, but there might be others, even potentially cheaper ones. So you can just hunt around, just make sure that they're supported by Linux. And the other thing is you need a Bluetooth device for the embedded side, Bluetooth radio for the embedded side. And this is one that I found is 20 bucks. Okay, so adding that up, 20 plus 10, 30, 30 plus 40 plus 15, taxes, you're looking at around anywhere from 90 to 100 bucks for this investment. There are other things which are optional, really, if you want to use this thing to kind of play around. Additionally, there are things that are listed, like for example, if you want to use faster sensor streaming, we are going to be using Bluetooth LE, but if you want to do faster sensor streaming and all, there's another option out here. Then you may want to package these things in nicer boxes and all if you want to play these things. But anyway, so baseline requirement is that you should have this board. Again, to recap, this board, no choice on this one, no options, other than if you know enough about embed, maybe you can use something else and buy the equivalent sensors. Either use your Android phone with something that gives you GPIO. You'll have to figure that out yourself. I think there's something called I202 or something like that, which is a board which plugs to USB of Android phones. So you can figure that out. In which so that will probably run you cheaper than buying this, but these are pretty cool platforms. So one of these. Questions? You know, I threw a lot of information.
Does it have to be Raspberry Pi B plus, absolutely, or because I have a B already?
Yeah, B should work fine. And in fact, I don't know about the A. There's also a cheaper model, A model. I haven't looked into it. It might also work fine. Just make sure it has a USB port and some enough GPIOs and to work with. So quite likely you're fine. You know, so now they have a version C, and I was reading at the differences in that, and the main thing that matters is it has now a lot more onboard flash, so you don't need a separate card for most things. Okay, and then I think depending upon what's the older version you have, if you have a version B or A6, it's the same processor. If you have something older, then the processor has changed and has become faster and all. But again, you know, should work fine. I know some of the earlier A versions, they were really alpha version, they had bugs. As long as you're aware what they are and cope around it, should be fine. Okay. Last year in the class, I used A6, and that was fine. Okay. The mistake I made last year was I tried to run Android on BeagleBone, and that was a total disaster. So this time around, we're going to stick with this plain Linux. So the way you work with these things, a typical modality is that the default thing is if you have, I'm assuming that you have some Ethernet setup that you have access to where you have a DHCP server running, so this can pick up a IP address, okay? And then you just work off that, and then you just remote log in SSH to that. If you don't even have the switch and all, you can always hook it up to your computer out here and do the internet sharing stuff. Both Windows and Macs have it, and that works fine. So other than when you, so you basically, short answer, you don't need the keyboard and all. You can also actually run VNC. Anyone heard of VNC, Virtual Network Console? You can do that, and then you actually can get graphics which are coming from these devices. So plenty of options. So short answer, no, you don't need the keyboard and mouse. Anthony.
What if you only have Wi-Fi? If you don't have Ethernet in your Wi-Fi?
So in that case, firstly, do not get BeagleBone because it has only one USB. Okay. With Raspberry Pi, you can buy Wi-Fi USB dongle also. They run around, again, $10 or so. Even cheaper. I think the cheapest one I've seen on Amazon is like $7 or so. Okay, so plenty of options there. Just again, make sure that the particular Linux release supports it. Now, one other thing I just want to mention, Raspberry Pi does not come with any memory card with no operating system. All you get is hardware. And then you have to download a disk image and burn the flash using that, which means that you have to have on your computer some sort of a flash reader, and that's the OS thing. If this idea of doing this spooks you, then seek help or go BeagleBone, which comes with an OS already installed. Now, even for Raspberry Pi, most vendors sell a higher cost version, but then they charge more, where they give you a SD card with a pre-installed operating system on it, but then they charge far more than what you can just, the cost of the memory card itself. So, but again, depends upon your comfort level. So the cheapest option again is just get the Raspberry Pi and just download the image and kind of work off that. It's pretty straightforward, good instructions for whatever your platform might be, but you will need a SD card reader on your computer. Again, I know all Mac laptops have it. I don't know about other things, but you can always seek help there. Other questions? Okay, so cheating, plagiarism. So since there are collaborative element to this class, plus things like surveys and things like that, so basically what my expectations are following, that any material you are submitting claiming to be your own should be work done by you, not from a prior version of this class, not by someone else, not by someone else who is dead or alive. It has to be truly your work. If you are in doubt, talk with me. At times it's okay to do so, or I'll tell you it's okay, but then you have to cite this thing. If you get, sometimes I may give you a homework problem, and then you may find that you explore and all, and a solution, some technical paper provides you the inspiration for the solution approach. That's fine. Going around looking for previous homeworks and all is not fine. So there are more details out here. You can look at it in case of an episode. And interestingly, in recent years, every time I have taught my graduate classes, I have always had episodes, okay? And that has created, I guess, problems for the department, school, and of course, needless to say, the students. So try not to, please. Person aiding in cheating and plagiarism, if also in the class, will be similarly equally penalized. Basically, the way it works is, if you're new to UCLA, we basically send the information to Dean's office, and then they interview you and look at the evidence that I provide and decide on that. I'll also say that all the cases that I had submitted were accepted as valid cases of cheating by the university and resulted in penalties ranging from suspension all the way to suspension. So don't do it. It's the very same tools which make cheating easy actually also make it easy to catch cheating. So don't do it. And again, in doubt, first talk with me. Piazza, now mentioned you can collaborate and all. So let's say I give out a homework and what a problem means and things like that. Those are valid things to discuss. What's not valid to say is this is my solution. Okay, so it's valid to discuss what the question is asking for, things like that. It's not valid to discuss specific solution or solution approaches for that. Questions? Okay. Impact of travel on class schedule. So unfortunately, all of us in faculty, we kind of also have a research hat. So occasionally we do need to travel for some professional meeting or other. One thing which has happened in recent years is that the school now has a very good online lecture recording system and all. You might have noticed that at the beginning of the class there was this thing about recording starting 3, 2, 1. So I actually record all my lectures, and then with a few days delay I kind of push them out to YouTube. Few days delay simply because I need a couple of hours to do the conversion. So actually, if you miss a lecture or something, it's a valuable resource, but it's a valuable resource for me because I can just record the lecture from wherever I am and then push it out to you. So there will be a couple of, as of now, it seems like there are 2 dates I'll be missing. One actually is next week, next Monday, and then another one is going to be the Wednesday of the first week of November. And in, for this one, I will make up by doing a recorded lecture. But I'll do it later, not this week. Instead, I want you to begin to set yourself up with embed and all. I'll hand out a little homework for that. A thing that you should do today is, or if you have, you are enrolled and serious about taking the class, get that $15 embed device, okay? Because it makes world of a difference to have it while you are exploring embed software than not. If you are only, if you are still on the waiting list, this is a decision you'll have to make. Right now, there is one open spot, which I'll fill today based upon the responses I have thus far. So I'll send a PTE number to one of you. After that, I really cannot speak. It really depends upon those who are enrolled and how serious they are or not. Okay, I'll be handing out a homework, which you'll have to start working on towards the end of this week involving embed. That $15 device is available in quantities of thousands across the different vendors, Mauser, DigiKey, these kind of things. So you should be able to kind of get it relatively quickly. Anyway, so that's this. So that leads to kind of an important announcement. No lecture on 13th. So a week from now, we'll make it up later. And a crucial task for week 1 is to get that embed and set yourself up with it. Okay, go to embed.org, sign up for it, begin to explore what's there. It's a pretty rich website. Actually, if you just Google for 202A or 213A, you'll find a lot of material by older students. So it actually makes my task a little bit harder because every time I have to come up with a new homework, I cannot recycle because the solutions are all there. But that's the penalty I'm willing to live with. Questions before we take a short break and move on to the next lecture. Okay, so how many of you standing there are enrolled? Okay, so priority of seating, enrolled students, okay, please. So firstly, I think if you're towards the bottom of the waiting list, you're not going to get in, okay? The waiting list was 33. My suggestion is that if you are not in the top 15, give up. You are not going to get in. It's highly, highly, highly unlikely. There are not going to be 15 out of 29 who are going to drop out. So we'll take a 5-minute break, but apologies, but there are plenty of other courses. Try 202C. That's an exciting course, covers a lot of similar technologies, but we are capacity constrained. Okay, so let's take a 5-minute break and then restart on the next lecture. Thank you.
I'm not in debating this, but I'm a PhD student here and I'm working in architecture. Do I have any chance to?
Your CSE?
CS.
I'll take you in. Okay. So you have you get the PD. Send me your, who's your advisor? Okay. So send me your student ID number and mention that you spoke with me. What's your name? Farnush. Okay. Yeah. So I'll send you. Okay. Cool.
Do you have extra lecture printers?
I got 65, man. They're gone.
And
but they're on Piazza, so you can.
Yeah. No. And regarding the project and all, when will you start handing out, topics?
It will probably happen sometime next week.
Okay.
But you, based upon the samples from previous years, maybe some inspiration comes to you.
Okay.
And the thing is, I'll create a live document and start putting stuff out there.
Okay.
So, okay.
Thank
you enrolled or?
Yeah.
You are. What's your name?
Art.
Art.
Yeah.
Okay. You are what? CSE?
Double E.
Double E. Okay.
Thank you.
So. Okay, so let's restart. If you have not signed this thing or put your name on it in case your name was not already on it, please do so. I'll keep it here. You can do it at the end of class. There were some other issues that were brought up, and I just wanted to go over that. Firstly, I'd said BeagleBone is not as preferred as Raspberry Pi because it has only one USB. And then I guess a student back there pointed out that you can always use a USB hub. And they run pretty cheap also, $5-6 or so. They just make the whole setting a little bit more clumsy to handle physically, but that's unless you're trying to deploy it in a setting where size the whole package matters, that works fine. You would need, USB adapters also need to be plugged in separately because USB port does not have enough power to power it. So it just makes it a little more clumsy, but you can. Another student had asked, he has some other board from TI and all. You certainly could use. Okay, so again, Raspberry Pi and BeagleBone and Intel were just meant as examples. They're actually popular and good, but almost every company, SMC and Qualcomm and all, they all have boards running Linux with GPIO pins and USB and all, and they are fine. So if you already have something, maybe you work in a lab, you already have something, you can use that. Usually they are bigger and all, and of course they don't have all this support group behind it. So if you kind of run into an issue, it's sort of a little bit into, you're going to be on your own, but you can use them. Okay, and older versions of Raspberry Pi, BeagleBone and all work fine for the most part. Occasionally they have, I think in case of BeagleBone, some of the older versions had some bugs, but again, these tend to be well documented. You can work around them. So just see if you already have something sitting. You could actually even, if you have an old PC lying around and all, you can use that, but now you're in the world which is nowhere close to being a embedded world. And also the critical requirement again is it doesn't have GPIO as easily, and that kind of complicates things. You can use the parallel port on the PC if your PC is old enough to have a parallel port as a GPIO, but unfortunately newer PCs don't have parallel ports. So there are other options. Okay, if you have something, talk to me. You can save some money on that one. Final thing was a question which was asked about, what about the project? Can I just do a mobile app? Okay, and the answer is no. This is not a mobile computing class. So let me explain. If you are doing an application-oriented project, what are acceptable things and what are not? Something which only touches this layer is an app which only touches this layer is not. If it's a foundational piece which could be used in conjunction with this part, that's fine. Like maybe, for example, you're creating a new sensor analysis service or something like that to which devices it's supposed to talk. That's fine. But if you're just developing an app, it's not. If you're just developing an app on the phone, even if it's talking to the cloud, it's not. Okay. So essential requirement if you are doing an application-oriented project is that this layer must be there. You may have this and this, but if this is absent, then it's not embedded, it's not IoT. Okay, so hopefully that kind of clarifies what the expectation is. On the other hand, if the nature of your project is a foundational piece, a tool, a service, a piece of software, then it could reside on any one of these, but you have to describe how it works with or assists an IoT system where this layer is there. Okay, because if this layer is not there, it's not embedded. Okay, so that's hopefully sort of clarifies kind of the expectation that I have. So this course is not about, hey, I'll just create a mobile app, but certain kind of, so I could imagine certain kind of foundational apps that might be fine. Like for example, maybe a new sensor or actuator service and whose control interface is on this app. That would work because now you're making the case that look, these devices talk there and then kind of provide this thing, and you'll probably provide an example of that happening. If on the other hand, this is just something working off using maybe even the sensors on your phone and doing something, that's just generic mobile apps.
If we have the Bluetooth thing there on the far left, and we have Bluetooth on the phone, what do we need the GPIO thing for the phone for?
In that case, you don't. But I will have some homework where you'll be hooking GPIO to this board to do some time synchronization. Okay. Other questions? But you can delay that part and kludge around it, okay, because some of those latter homeworks I also do it in teams, so you may have access to your partners. Okay. Yeah. Another question which was actually asked by Anthony, which is the waiting list number that you see on URSA, is that the official waiting list number? Answer is I don't really know because I have to go by that priority, and so Mandy from Diana's office, she has kind of given me a spreadsheet that I have that list. And the final comment on that, I had said I had 29 enrolled and 1 free spot, and there was a PhD student who spoke with me and just grabbed that slot. She has the highest priority, so now the class, after I gave her the PT number, it would be back to 30. So basically at this stage people have to drop. Now again, as I said on previous occasions, usually I have maybe 10 or so drop. Okay, I have a reputation of being a hard instructor. This course has a reputation of being a demanding class, a lot of work, so people drop out. Yeah, Anthony can vouch. You can vouch for it, right? A lot of work. Okay, good. He wants to move up the waiting list. Okay, so in any case, so people do drop out. But having said that, being realistic, I think if you're within the top 10, 15 of the waiting list, you should be able to get in. So I think, as I recalled, as of now, there are no PhD students on that waiting list that I have, unless someone kind of enrolled more recently. And the second thing is that I don't recall there were any 2-year, second or higher year CES students either. So it's basically everyone else is there. So my guess is that second year students, second year MS students from other areas of EE or CS, they were, I mean, if there is any, I think we had sort of used them, that list to the best of my recollection. They should probably hang around, and if you're a first year CES student, you should probably hang around and wait it out for a week, week and a half. I think others probably will not get a chance. Okay, so second lecture. So this one we'll kind of continue on to Wednesday also. So I wanted to go over some of the background material, challenges, kind of what kind of things happening, why, kind of a bit of a historical perspective also as well, to kind of put this whole field in perspective a little bit for you. So computing has always been driven by kind of trends, and these trends are often given names and become laws and become famous. And one of the most famous one in our discipline is the so-called Moore's law, which basically says that computing resources double every 1.5 years. Less well known is Nielsen's law. Nielsen is the same Nielsen who Nielsen's rating for TV and all that. Okay, the same guy. He had sort of shown that the high end users bandwidth grows around 50% per year. So a slightly lower rate than Moore's law. That means our computing improves faster than connectivity. Okay, but that trend also seems to be holding pretty well also. Putting these things together, there's another law called Bell's law. Gordon Bell, the famous computer architect, and he basically said that roughly every decade or so, because of a confluence of these progresses, what happens is things reach a threshold where a new class of computing systems emerge, and a new industry emerges around it, and so on and so forth. And if you kind of look back historically, that indeed kind of seems to be happening. Every so often we kind of suddenly see a new class of computing systems emerge. So we kind of started with mainframe and the mini computer and workstation, and I was actually at a talk recently at UC San Diego, and this was by someone who was actually describing software for Internet of Things kind of setting, buildings with sensors and all. And he was saying that there are a fair number of his users which are still using DEC VAXes, which are 1970s machines before, I imagine all of you were born. Okay, so I guess some of these things are still lingering around. PCs and routers and cell phones and smartphones, and now we are kind of somewhere out here, Internet of Things, and I guess looking forward a bit ahead, I think more autonomous stuff is certainly, we are kind of seeing the early stirrings of these things already there. So computing has been changing. Another way of looking at is that the ratio of devices to, or whatever, ratio of computers or CPUs to people. So we were in an era where kind of a mainframe serving hundreds of people to one where we kind of headed towards 1:1 PCs. And now we are in an era where number of computers to people is much, much more than one. I think just looking around your own life and how many CPUs you can classify as belonging to you, the number is amazingly high by the time you kind of add various appliances in your vehicle and your stuff in your home and all. What is also happening is that computing systems are getting more and more capable of interacting with the physical world, so sensors and actuators and all. They are becoming smaller and mobile and kind of part of things, so like sensors inside shoes and stuff like that and all. And then final bit is that they are getting distributed and connected. Okay, so these are all kind of representative of that. Whole bunch of embedded systems, things that you won't think of computers or but the embedded computers play a huge role. I mean, appliances and vehicles and toys and every imaginable thing that's out there. So all this convergence and all. Now, people have always dreamt about kind of smart stuff inside things. Back in late 80s, early 90s, Xerox PARC, which was probably one of the most dominant computer science laboratories that ever existed. They had this project called Ubiquitous Computing, and a guy called Mark Weiser who kind of put out this vision of sensors and computers and kind of the fabric of our surroundings and all. And I grew up in that era, and kind of it was it tickled the imagination of a lot of computer scientists and all, and kind of led to a lot of work. And these new phrases like ubiquitous computing and pervasive computing, they kind of came out from that era. Then late 90s, another sort of similar trend started, and which actually UCLA was pretty dominant in. In fact, Professor Kaiser, who's doing the 202C, was one of them, and that's this notion of wireless sensor networks. Okay, so this is the idea that, I can now, while my embedded systems cannot be connected to the internet, but they were certainly at that stage capable of talking to each other. So what soon emerged was tiny sensors with little radios talking to each other, and then talking and monitoring something. And people kind of explored all sort of stuff, monitoring forests and volcanoes and buildings and all. There's a building here called Factor Building, which is somewhere on this side of campus. That was densely instrumented. We had a big center here called Sense, which is that building which is in the courtyard of Bolter Hall. So anyway, a lot of stuff happened, and UCLA, UC Berkeley, some groups in Europe really helped this technology kind of come about. Now, a lot of startups happened, all of them failed. So again, kind of things were perhaps a little bit earlier than in time, but also I guess the value proposition wasn't very clear outside captive markets. So it took off in like oil companies trying to monitor petroleum processing plant or ships and all, but kind of as a wider technology, it really didn't sort of pan out to the same extent. Scientists used it, remain a specialized instrument, but didn't become something that we see in our day-to-day life to the same extent. But then in the interim years, what has happened is a few additional technology trends have come. One is the spread of internet. This vision of IP everywhere, that is, everything is on the internet, has always been around. Jokingly in computer science, we often deride it as IP to the light bulb thing. Okay, that everything is on the internet. Anyone knows who that gentleman is? Huh? Vincent Cerf. Okay. Who is Vincent Cerf? Okay. Who's Vincent Cerf? Anyone? Come on, guys. On 2 counts, you are failing. Okay. Number 1, he is arguably the father of the internet. He created TCP/IP. Okay, which is what you use day in and day out. Second thing, he's a UCLA alum. Okay, so more so. Okay, he's the guy sitting in this building, did this stuff. Okay, anyway, So he's, I think, currently at Google. They're Google's chief scientist, something like that. Okay, chief internet evangelist. Anyway, so this vision of everything being on the internet been always been around. I was looking at like just googling for like how much of Earth is accessible by internet, and pretty much some parts of North Korea, which is kind of essentially a closed society, you can get internet access everywhere. Okay, so connectivity everywhere. So now, what was SensorNet thing, which is embedded and connected, really became embedded and connected everywhere. Everything connected and all. So basically, the proposition at this stage is everything has a computer because processors are so tiny and low power and all. The internet is everywhere, and all the computers have a network interface of some form now. Okay, there are chips where you have literally radios on the chip, processor, radio, memory, kind of a self-contained computer on a chip. That's, you can buy this stuff now. So all of this, as it began to come together, we began to see kind of a new class of things, even more sophisticated than what the sensor nets and standalone embedded systems began to emerge. Some of the plots I picked up, internet connected devices. I'm seeing numbers like by 2020 there would be like 50 billion devices on the internet. Okay, and by the way, that 50 billion is a lot more than a traditional IP address space, which is roughly 4 billion, not even that. So which is why we are transitioning to this IPv6, which is 128-bit addresses, so that we can address every whatever subatomic particle that there is in the universe. More connected devices and people. Many years ago, we crossed that boundary, and at this stage, I mean, things are dominating traditional computers. Okay, so so everything computerized, everything connected. The other thing which also happened, two other things, smartphones happened, or particularly really decent smartphones, really mobile computers, if you may, with sensors, short-range radios, and full-blown networking stacks. Initially, these sensors were put there just for user interface purposes. Accelerometer was put into the phone so that you can reorient the phone. Light sensors were put into the phone so that when you bring the phone to your face, then the screen would shut off. But pretty soon people discovered that these sensors can do other things, and actually a whole ecosystem of ideas and applications and services kind of developed around it. Smartphones happened. Another one is cloud services. Okay, again, I mean, looking back over the past decade, I mean, these are a couple of very dominant trends. Lots of data that needs to be processed, stored, computing as a service kind of models. All these things begin to come together under this general umbrella of cloud services. So we could, using embedded systems, we could collect and control the physical world. Using smartphones, we can visualize them. We can use these phones as a gateway. Using internet, we can transport this stuff, and using the cloud, we can archive, process, analyze, all these things. So all the pieces, I guess, in recent small number of years, all the four pieces really have sort of matured to the degree that you could do these things. If you look at phones, I mean, the kind of stuff people are able to infer from the phone is just amazing. Okay, and of course, the number of type of sensors in the phone have been improving, but also kind of just really, besides gateway, they themselves are sensor devices. Whole bunch of apps and all. Okay, I mean, a lot of them health related and all, which have emerged. Okay, in many cases they rely on sensors that talk to the phone. So going back, that device tier is very crucial to it. And in fact, I guess this year we are really seeing kind of the bigger players, Samsung, Apple, and all kind of really coming out with stuff which kind of is after the device tier. Cloud services for sensors, a whole bunch of things have emerged. Services which can let you store lots of time series. Sensor data tends to be time series oriented. Visualize them, create rules on them, trigger action rules, things like that. So a whole bunch of stuff. Xively, ThinkSpeak, IFTTT, Sensor Cloud. I mean, to sit down, there are probably like a few hundred of these things around, oftentimes in the same space, all kind of enough VC money floating around to kind of nurture them and all. So a lot of cool stuff happening. So these four pieces that I mentioned, the embedded stuff, the mobile stuff, the networking things, and the cloud, they kind of really are what have sort of come together to create what in some senses we see around us today, Internet of Things or whatever you might call it. I like to think of them as that what we now have are systems which are capable of digitizing and controlling our physical world, ourselves, our spaces. A day is not far off when these things will also be even more intimately connected to us. Okay, there's already a lot of cool stuff happening in medical school and EE department, for example, with sort of implantable stuff inside brain and all. Okay, so artificial eye, work in bioengineering out here, or artificial memory prosthetics, and a lot of these things kind of rely on communication with the outside world. So we are seeing this stuff getting into things in ways that pretty hard to imagine. So what these systems do is, through sensors, they get data. From that data, they make inferences about what is happening in some system, the physical world of a biological system, and based upon those patterns, then they create actions, interventions, control actions, things like that. And you see this thing in a whole bunch of different domains. So that's what we have at this stage. Embedded systems in large numbers on the internet. And of course, media has picked this thing up. Just from earlier this year, some headlines from various newspapers. But there's a contrarian viewpoint also, and I think I would be remiss if to not bring that out. So one thing in computer science is a lot of stuff we do has been around for a long while. So there is this quote out here. It's actually a pitch for funding to venture capital, which was given back in 1986. And if you read it, it's not very different than a whole bunch of companies, what they're doing right now. It's a company called Echelon, which was actually founded by one of the guy who was the second CEO of Apple. And this kind of talks about kind of sensors and things at home, kind of a smart home kind of vision. And of course, the technology pieces weren't there. Okay, so I think we have all conceptualized. I mean, thanks to watching, I guess those of my generation grew up on Star Trek, and also we were always kind of these kind of ideas have always flown around in imagination. And I think it's only now that all the relevant pieces are there that we can approximate those ideas, or even do better in many cases in ways we couldn't before. Some people, so there is this company called Gartner, which actually does technology studies for investment market and all, and they have this cute little chart where they show that how different technologies kind of go through this thing. There's a hype phase where they are being built up, they reach a peak, then there is a letdown, things fall. Then after a while, people discover that perhaps some of them are still useful after all, and then they kind of ride a stable curve. And they do this thing by kind of looking at what is happening in the investment market and kind of media and stuff like that. Guess where Internet of Things is? It's here at the peak. So what it means is that it's probably going to fall. Big data was there last year according to the study, and so anyway, so just wanted to bring that point out that that at the core level, these are not new ideas. Oftentimes, ideas reach a certain fever pitch because the rest of the economy, society, and technology kind of just reaches the right point, and then everyone takes a pause, and then some of these things kind of trickle through. Now, having said that, the idea that we will have smart autonomous things in the world around us is something which I think it would be very hard to make a case that it will not happen. It's whether this wave succeeds or be something future, whether current generation of companies are the one who make it happen or some future, who knows. I mean, our technology industry is fraught with failed efforts. They were either too early or too costly or just didn't get the things right and things like that. I remember I was watching a few months ago the Daily Show, Jon Stewart comedy channel. I don't know if any of you watch it or not. So this guy from MIT Media Lab, a researcher like me, very excited, and he was showing all his toys about embedded stuff and IoT and all. And I have this like medicine bottle which remembers whether I opened the cap and took a tablet or not. And he is very excited. And Jon Stewart says, but all of it is doing something which I can do myself, or kind of like a total letdown, and then this computer scientist begin to stumble and all. So I think oftentimes we go excited by the technology and not kind of realizing that is it really solving a crucial problem or not. And I think a lot of stuff is of that nature, no doubt. Having said that, at this stage, it's probably fair to say that things like autonomous vehicles or vehicles which are increasingly smarter are happening. It's not the question of whether, I mean, this technology is just going, has penetrated level. And there are a lot of other things which we can put into that category, smart meters and all, have happened to the level, all the fears aside. So, I mean, famous last words aside that, but maybe, I mean, this is some, despite all of these things, I mean, this is probably a technology which, at its core, is something pretty interesting and worth studying. So what we have at this stage, I mean, I think when I started out teaching embedded systems many years ago, it was just basically a tiny standalone system. Okay, power, size, those were the issues. But I think at this stage, to effectively learn about embedded systems, one really has to kind of look at in this whole context of the four pieces: the cloud, the network, kind of the mobile stuff, and the embedded stuff, or which kind of I classified into those three tiers: the device, the gateway, and kind of the cloud. So lots and lots of applications. Industrial automation actually has been one of the very early adopters. Tasks here are easy. In fact, wireless sensor networks also penetrated here very well. The task here is easy is because these are very well managed systems. They are isolated. They are not exposed to grandmas and others. I mean, these are professionals creating a system for a very specific purpose. And a lot of stuff has happened. There's like specific standards and all, which are not as commonplace, but things like wireless HART and 802.15.4 or Zigbee, these are kind of wireless communication standards which emerged in order to cater to this market initially, and then kind of later migrated. There are a whole bunch of other things which have been happening there. Home area networks is actually also a very old topic. I mean, having convenience at homes and all were always something that people tried to push at the richer people, and the early technologies were very clumsy and painful and unreliable. Things like X10 and Insteon and these kind of things, and they came and had some stiction and then went out of fashion. Home security systems were probably the one place where they found most thing. But again, in recent years, a lot more stuff has begun to happen. I mean, our home security systems are on the internet. There's a lot, sensors went wireless and all. There are, again, standards catering to this market, Z-Wave and 6LoWPAN and stuff like that. So again, a reasonably well-established industry at this stage. I think the convenience and the reliability has risen to a level that things have reached a point where the adoption is ticked up. And you can buy a lot of these kind of stuff at Home Depot and all. Personal area networks, again, after a lot of false starts and all, at this stage, a lot of people are using kind of some sort of smart wearable devices and all. Potentially many of these per person. We saw the emergence of Bluetooth Low Energy as a result, so that's kind of become a de facto last few inches of communication modality. And then a whole bunch of network devices. I mean, this is the Nest thermostat, which gained a lot of media attention and stuff like that. And in this layer, these are somewhat higher end devices, so they still tend to use Wi-Fi and those kind of things. So, bunch of technologies out there. Lots of other examples. Okay, some of many different permutations. Sometimes devices talk to some sort of a network gateway. Sometimes devices talk to a phone and use phone as a gateway. The phone is pretty versatile. It can be a gateway. It can be a user interface device. It could be a device which can give you feedback and exercise some control. It can even hang on to the data. It has much more memory than stuff sitting out here. So it's pretty versatile. And then there are things directly connected. Most of any car pretty much at this stage you buy at, let's say, 30K plus range, they're kind of always connected. Tesla is kind of rather renowned for that, but even kind of a lot of low-end cars, lower end in that spectrum, have been doing so. There is actually a cute little website called IoT List, where what people do is they kind of essentially those who are running crowdsource funding campaigns and all, they kind of, this is a directory of them, and I kind of just browse through it and all, and there's a lot of cute stuff. Most of them will probably not do anything. I mean, at the end of the day, how many baby monitors and things like that you can have, but nevertheless, kind of a flourishing market of ideas out there. many, many more. What's beginning to happen, I guess, at some level is collectively, all of these things are systems which are really seeking to provide a couple of things. They are seeking to provide us pervasive awareness, as in awareness about what's happening to us, our physical world, things that interest us, wherever we are, and also kind of the state of things. And increasingly also interventions. That is, it's not simply enough that I know my things are not good at my home. I should be able to do something about it. Okay, so somehow actuate, somehow control it. So we are seeing stuff moving away from simply sensing to also kind of controlling stuff. So this, what you see out here is that really at the physical plan, sensors, actuators, and then this whole ecosystem that I kind of talked about before sits on top. It does sense, make inferences, decide, act, kind of many control loops at different scales. There are control loops at low level, there are control loops at the high level, sometimes human being is involved, sometimes it's autonomous. All these kind of things are happening, and what's really sort of this assemblage of technologies that I have mentioned along the way sort of comes together in this. There are, in some application domains, these are happening in a very systematic way, very sort of, there are communities that have developed pursuing specifically a class of systems in that. One which comes to mind quite a bit are mHealth systems, so wireless health system. Professor Kaiser's course is actually a lot about this. He has a center called Wireless Health, but there are a lot of other activities as UCLA outside the umbrella of that center also, which basically is in this notion that there are sensors monitoring data, monitoring things which are relevant, from which you can derive markers of health. Okay, they could be physiological sensors, but they need not be. There are a lot of other things from which, through appropriate algorithms, you can distill out markers of health. Whether someone is smoking, these things like, let's take the act of smoking. You can make inferences about it if someone is spending a lot of time at a known area which smoking happens, and then the walking patterns and all, where there is spacing and all, could come together and make an inference that, okay, smoking was happening. Location is a big thing. Studies have shown that motion patterns begin to detect changes in health status of people with Alzheimer and Parkinson's. So even sensors you may not think of, health sensors, begin to kind of provide information which is relevant. And then on top of it, to make sense out of that data, then you need to develop models. Models can come from scientists, models can come from a purely data-driven approach, and then all those models can then further kind of result in status information, notifications, and more importantly, often autonomous sort of interventions, controlling things back. Someone has fallen, or maybe some chronic health that you're monitoring is getting worse. One big study that Professor Sarafzadeh out here has been engaged in is people who have heart failure. Okay, it's a congestive heart failure. So it's a chronic, once you develop it, then you have to keep a lot of health parameters in mind and all. And this is something where, like, if things don't happen, they have to again rush back to the hospital and all. So being able to monitor what patients are doing while they're leading their daily life becomes very important. So mHealth is focusing on this. Continual monitoring of health-related parameters, distilling health markers, and then using that to create models and using that to develop interventions. Another domain where this stuff is happening a bit is buildings, for purposes of security, sustainability, and things like that, where people using sensors for occupancy, energy measurement, and things like that, you kind of do, again, make inferences, predictions, and use that to control stuff. A very active area of work is better control of HVAC systems. So HVAC systems consume a lot of energy. So buildings consume around 70% of electricity and some 30-40% of energy in this country, and other countries are kind of similar. And of that, HVAC probably accounts for half or even more in kind of most cases. And it turns out that HVAC system control, particularly in buildings like these, are designed in a pretty traditional, archaic way. They have some assumptions about when the building is occupied or not. There are regulations about how much ventilation should be depending upon maximum occupancy and all. So, like, for example, there is a regulation about airflow per person. Now, because we don't have sensors for how many people are actually in a room, so airflow is set on the basis of maximum occupancy of a room. So even if the room is only a third occupied, the airflow is still maximum. It has two issues. Firstly, that overkill wastes a lot of energy, and secondly, it actually affects comfort level. Okay, so a lot of attention in the building space happening, new conferences and all at this intersection of building science and computer science, and kind of a lot of interesting work happening. So these are domains. There are others. Transportation is another one where our transportation system literally is being revolutionized by sensors and actuators. Okay, there's tons of cool stuff happening. Pretty soon we'll have cars talking to cars, cars talking to traffic lights, cars talking to sensors on the road. I mean, these technologies in some shape and form are there. Self-driving car, but also cars coordinating their driving by talking to each other and keeping the distance, and then they can kind of have a lane which is just for robotically driven cars with no humans allowed, kind of things. So a lot of ideas floating around. I was hearing a talk by someone from BMW, and they said, what if the car knew what was coming a few hundred meters ahead? They could actually optimize things, fuel efficiency, and a lot more. Right now, that those kind of information just isn't there. Cars react to what they are seeing; they don't predict. So that kind of stuff. Going back to this model that we had before, so the device tier, the gateway tier, and the cloud, and kind of our physical world is out here, and we kind of interact with them through these devices. There's a whole bunch of technologies that have emerged in recent times which are relevant out here. So in this tier, we look at very low-end processors, 8-bit, 16-bit, maybe very low-power 32-bit stuff has now begun to emerge. We have platforms like Mbed and Arduino and MOTS. MOTS was something which came out of UC Berkeley, became very popular. We have operating systems which are more on the simpler end. Mbed is partly an operating system as well. FreeRTOS, Contiki out of Europe, very popular there. TinyOS out of UC Berkeley. And languages tend to be more of the systems type languages, C, C++, Java for the most, C, C++ for the most part. Then you have a whole bunch of connectivity things, physical layer things, so Bluetooth, LE, Zigbee, Ant Plus. This is a radio which you will find in a lot of health sensors. Whenever you go to gym, and if you have a wireless sensor strap for heart rate and all, quite possibly it's Ant Plus. Wi-Fi Direct. This is kind of a for two devices to talk, two peers to talk to each other. Z-Wave, very popular in home settings. Wireless HART, and then higher layer stuff on top of it. Not just the physical layer part, BACnet is used in buildings. In fact, this building has a whole BACnet network. All the sensors and all speak BACnet. It's a object-oriented kind of a paradigm on top. Modbus, 6LoWPAN. This is kind of the IPv6 optimized for these kind of settings. Next tier up, we begin to have more powerful processors. So now we are suddenly into the world of x86s and MIPS and Apple AXs and Samsung processors and so on and so forth. Platforms are more powerful, capable of running kind of a real operating system, if you may, and bar none, they are 32-bit or 64-bit, increasingly multiple cores as well. At this stage, you begin to see also other languages, kind of like Python and JavaScript and all also emerging because they make the development easier. In fact, a lot of stuff happening, and then also middleware type of things. Node.js is kind of something which came out of event-driven programming of web-based systems, but is found home in these kind of devices quite a bit as well. Next year up, we are into the world of standard technologies, Wi-Fi, 3G, 4G, LTE, TCP/IP, and then there are more specialized protocols. There's something called AMQP, which is a messaging protocol, which kind of really lets you have applications over the internet talk to each other in much more complicated patterns. MQTT is something which is a higher layer protocol specifically for time series type data, sensory data, and all. And then lots of cloud services, and then in many cases you can rent computing out here to run your own service. So it's like the third. You can have your own custom component running in the cloud fairly easily at this stage. There are a lot of give you free virtual machine instances, or you can buy them very cheaply and then kind of have your system really have these three components, one of them running out there. And there are, in addition to kind of programming languages and stuff like that, there are specialized databases catering to time series type data and all, like OpenTSDB, Open Time Series Database, for example, as well as kind of a lot of frameworks which make writing and talking to the lower tier pieces kind of more easier. So at this stage, a lot of software support is there, but more importantly, a lot of software support keeps emerging as well. There are a lot of companies and all who are really doing the foundational work. They're creating new types of time series databases. Still, new kind of analytics happening out here, things like that. So there's a lot of interesting stuff which is very, very actively happening. And one thing I wanted to mention was why this gateway. So why don't we have the embedded devices directly talk to the cloud? And the thing is, it's basically eventually about the technologies, which is the devices which are embedded, wearable, implantable are usually significantly size and power and cost constrained. They have to operate on tiny batteries. Sometimes they have to just harvest energy. Sometimes they're disposable. Okay, in fact, like a lot of these tiny devices come with rechargeable batteries which have a finite lifetime. You can recharge them only so many times. So they're disposable. So just from a user experience perspective, energy is a significant constraint. So ramifications is they cannot hold data for long. They can't do much processing on the data. They cannot afford the type of radios that you need to directly talk to the cloud. Okay, certainly not cellular, but not even Wi-Fi. I mean, these are just way too power hungry. They may operate intermittently, and they provide very constrained programming environments and all. So you really cannot do complicated stuff there. So gateways help overcome all of these. They bridge communication, and that's certainly the most critical aspect of the gateway functionality, but they can also provide storage. Like the connection to the cloud may be gone, but my Fitbit doesn't have enough storage, so it dumps the data to the phone, and the phone can store it. They can do some processing before sending the data to the cloud, which has, like for example, no point sending tons of raw data out there. Perhaps I can do some distillation, compression, extract events, send those things out. It helps improve reliability, makes things more cost effective, and very crucially, they could also be a privacy shield of software. I could take Bluetooth LE sensors that you get right now, okay. One key difference from standard Bluetooth is that they don't require any pairing. Anyone can hear them. And therefore, they are a privacy, they present some privacy challenge, but you can do this kind of stuff on the gateway. So the gateway could act as a firewall and provide the requisite privacy. And very crucially, you can program more easily out there. We saw that the type of languages and frameworks available there are a lot more powerful. So typical stuff, and this is the last slide for today, is that if you look at typical system, I just picked up a course project, undergrad course project out of UC Berkeley, where they basically made a device which would hook up to your car and kind of collect raw data, and then an analytics service which kind of gives you your driving style and recommendations and stuff like that. Okay, the specific details don't matter. The main thing is the car connects to this device, and that's a wired connection. So this device really plugs into the car. Bluetooth to talk to the phone. Phone is using Wi-Fi to 4G to talk to the cloud. Okay, so in this case, the model could be when your phone stores the data, and then when your car pulls into the home, then it uploads it. Okay, or maybe the phone uploads it when you plug it to the charger, things like that. So a lot more kind of models can appear from this. So I'm going to stop out here. We'll continue this particular slide set on Wednesday.